state transition matrix, the definition of the matrix is like it changes the state from one state to another state. Like the initial state x of 0 at t equal to 0 is driven to the state x of t at time t. So, this happens, initial state x of naught is transferred to the state x of t at time t with the help of a matrix E of at. That is why E of at is known as STM, state transition matrix. So, this E of t is equal to I identity matrix plus at plus 1 by factorial 2 a square t square plus 1 by factorial 3 a cube t cube plus and so on. So, this is also designated by pi of t, and this state transition matrix, it also can be expressed in the form of Laplace inverse of Si minus A inverse. So, with the help of this matrix, the state of the system from x of 0 at t equal to 0 will be transformed to x of t at time t. This is known as state transition matrix. So, how to obtain the solution when state equation is given? State equation is given by x dot is equal to Ax plus Bu. So, there are two methods to get the solution when system is described by state equation. Number one is Laplace transform approach to get the solution. So, in this approach, consider this state equation x dot is equal to Ax plus Bu, and now you apply Laplace transform to this state equation. Then this is x derivative. So, you have s x of s minus x of 0 initial condition. This is equal to a x of s plus b u of s. This is input vector. Now, you can take a of x of s this side, and you can rewrite this equation as Si minus a into x of s is equal to x of 0 plus b u of s. Now, x of s is equal to, take this to the other side, Si minus a inverse x of 0 plus Si minus a inverse b u of s. So, now I would like to get the solution is nothing but time equation x of t, the state of the system at time t. So, I must apply inverse here, that is Laplace inverse Si minus a inverse x of 0 plus Laplace inverse of Si minus a inverse b u of s. So, this is method 1. When you apply Laplace transform and x of t, again you get with Laplace inverse. So, this part of the response is called ZIR, that is 0 initial response, and this part of the response is called ZSR, 0 state response, and this ZIR, the first part of the equation, this is due to initial conditions that exist in the system, and the other part ZSR is the zero state response. This is always due to input that is applied at time t. So, this is method 1 to get the solution is nothing but x of t. It consists of two parts, ZIR and ZSR. This ZSR is due to the input and ZIR is due to initial conditions. Method 2 is to get the solution when state equation is given. This method is known as classical method. Here we use state transition matrix. So, x of t is equal to e power a t x of 0 plus integral 0 to t e power a t minus tau time constant b into u of tau t tau. So, when state equation is given, how to get the solution is nothing but x of t. So, to get that, the method 2 is a classical method, and x of t is given by e of a t into x of 0. This is initial response, 0 initial state, plus integral 0 to t e power a t minus tau to b u of tau. So, this portion can be treated as phi of t minus tau. First part of the solution is known as 0 initial response, and the second part of the response is known as 0 state response. So, this part is due to initial conditions, and here you can find e of a t, that is known as state transition matrix. So, we can consider phi of t as a state transition matrix, that is nothing but e of a t. This is equal to Laplace inverse of Si minus A inverse. So, this is known as state transition matrix. It is the matrix which transfers the state of the system from x of 0 at t equal to 0 to x of t at time t. Now, when you compare 0 state response, integral 0 to t phi of t minus tau b u of tau, this is input vector, d tau is equal to Laplace inverse of phi of s into b into u of s. So, this part is a 0 state response, and x of t is equal to e of a t into x of 0 plus Laplace inverse of this part phi of s into b u of s. This is the total solution or total time response, and the first part it is known as 0 initial response. So, the system, if it is homogeneous, that means the input is 0 for homogeneous equation, then the x dot, the state equation will have only first part of the equation a into x. So, for this, if you want to have x of t, that is solution, it is only 0 initial response you have. This is nothing but e of a t into x of 0. This is the case when the given equation is homogeneous. So, the properties of state transition matrix, because this is the matrix which is transferring the state from x of 0 to x of t. It is also treated as phi of t. It has some properties while solving the any system that is described by state equation. So, number 1, phi of 0 is I. This is an identity matrix. Phi of 0 is the first property, and that is equal to I identity matrix. The second one is phi power k of t. This is equal to e power at, this is state transition matrix, whole power k, and this is equal to e power a into kt. So, this can be now written as phi of kt. So, this is the second property of the state transition matrix, and the third property, phi of t1 plus t2 is equal to phi of t1 into phi of t2, and the fourth property, phi of t2 minus t0 into phi of t1 minus t0 is equal to phi of t2 minus t1. So, these are the properties of state transition matrix, which helps to find the solution when the system is described by state equation. So, how to obtain the complete solution, or is nothing but time response when the system is described by a state equation. When you look at the equation, x dot is equal to A matrix times x. So, there is no second term in the state equation, that is the input vector part. So, we can consider the given system as a homogeneous. So, when you consider this as a homogeneous, then the solution x of t is equal to e power at into x of 0 alone. So, this is nothing but 0 initial response, and that is only available if the system is homogeneous. So, this can be phi of t, that is state transition matrix. So, we should know what is e power at. This is given by e power at equal to Laplace inverse of Si minus A inverse. So, we need to determine this Laplace inverse of Si minus A inverse, that is nothing but state transition matrix. So, to know this, we should have Si and A. So, what is Si? Si is an identity matrix with S as a diagonal element. So, this is a 2 by 2 matrix. So, this is Si. A is already given in the system, it is equal to 0, 1, minus 2 and 0. So, now we should have Si minus A term and then inverse of it. So, Laplace inverse of Si minus A. So, you need to have a subtraction of this Si minus A. So, this is given by S by S plus 2, 1 by S square plus 2 and minus 2 by S plus 2 and S by S square plus 2. So, the denominator is same for all the terms. So, this part, the part of this one is Si minus A and then inverse also, that is why you have a denominator same for all the terms. So, now you need to have a Laplace inverse of each and every term. So, this is given by Laplace inverse of S by S square plus 2. So, this is given by cos root 2 t, then 1 by root 2 sin root 2 t second term minus 2 sine root 2 t and cos root 2 t. So, after determining Si minus A inverse, now you have to apply Laplace inverse of this one. So, it is like S by S square plus A square Laplace inverse, that is cos A t. So, you have 2, so cos root 2 t you get, and for this second term it is 1 by root 2 sine root 2 t and all. So, this is considered as phi of t because it is a state transition matrix. It is also nothing but e power a t. Now, to get 0 initial response, that is nothing but you have to multiply the state transition matrix with x of 0, that is initial condition. So, x of 0 is given by 1 and 1 here. Now, you need to multiply this e of a t or phi t, what is obtained, you should multiply this by x of 0. So, phi of t is given by this and x of 0 is 1 and 1. So, the resultant of this will be cos root 2 t plus 1 by root 2 sine root 2 t first term and minus root 2 sine root 2 t plus cos root 2 t. So, this is the product of phi of t and x of 0, and the output of the system y is equal to, it is given c into x. Now, x of t you could get here phi of t. So, this is given by 3 by root 2 sine root 2 t. So, this y you obtained from y is equal to c into x of t. This is the state equation, output equation in the state model. So, c is given by here 1 and minus 1, these are the C matrix. Then x of t is this one. So, you need to multiply this 1 and minus 1 with the term you have got x of t, that is nothing but cos root 2 t plus 1 by root 2 sine root 2 t, then minus root 2 sine root 2 t plus cos root 2 into t. So, multiplying the c with x of t, which is nothing but 0 initial response, leads to this equation 3 by root 2 sine root 2 into t. So, this is the way to get the solution. We should find out state transition matrix first and then multiply with the initial conditions, you will get x of t. So, that x of t you need to multiply with the C matrix to get the output equation. This problem is again to get the complete time response when the system is described by state equation. When you look at the state equation x dot, you have here ax plus bu. So, this is not homogeneous system. So, we need to have both 0 initial response as well as 0 state response for this given system. So, initial conditions also exist here, x of 0 equal to 1 0. So, the given state model we say that it is non-homogeneous. So, the complete solution is consist of 0 initial response plus 0 state response. So, 0 initial response is nothing but state transition matrix E of a t power a t and x of 0 we should determine. So, for this you need to have Si minus a and then inverse and Laplace inverse. So, to get Si minus a first, it is a 2 by 2 matrix. So, you get S minus 1, 2 and S plus 3, this is Si minus A, and I want to get Si minus A inverse for this, Si minus A inverse for this. This is like it is 2 by 2, so easy to get Si minus A inverse. You have to have adjoint Si minus A first, that is by interchanging this diagonal elements, their position S plus 3 and S, and sign of this diagonal part you need to change, minus 1 becomes plus 1 and 2 becomes minus 2. So, this is adjoint A or adjoint of Si minus A. Now, mod of A, that is determinant of A, you should get. So, that is the determinant of the Si minus A matrix. So, you will get S square plus 3S plus 2. So, this is Si minus A inverse. Now, Laplace inverse of Si minus A inverse is required for this 0 initial response, and this is equal to Laplace inverse of S plus 3 by that S plus 1 into S plus 2, first part of 2 by 2 matrix, and the second part is 1 by S plus 1 into S plus 2, the denominator is same for all, minus 2 by S plus 1 into S plus 2, and the last one is S by S plus 1 into S plus 2. So, for this Laplace inverse you need to find out. So, to have that you need to apply first partial fractions and then Laplace inverse for this. So, the first component of 2 by 2 matrix, you get 2 by S plus 1 minus 1 by S plus 2 when you apply partial fractions to this matrix, and the second component is 1 by S plus 1 minus 1 by S plus 2, and the third one minus 2 by S plus 1 plus 2 by S plus 2 minus 1 by S plus 1 plus 2 by S plus 2. So, now it is easy to apply Laplace inverse because we need to get e power at. This is nothing but phi of t, and the resultant you get here when you apply Laplace inverse for each and every term. So, this 2 by S plus 1 can be 2 power e power minus t minus e power minus 2t, that is the first component, and the second one, this part is e power minus t minus e power minus 2t. Now, the first component in the second row is minus 2 e power minus t plus 2 is already there, this is e power minus 2t, and the last component is minus 1 e power minus t plus 2 e power minus 2t. So, this is the state transition matrix you get. With the help of this, the state of the system is transformed. So, e power at you got. Now, to get 0 initial response, I must multiply this with x of 0. So, the 0 initial response is the matrix which you obtain phi of t should be multiplied by x of 0. So, this can be taken as it is, and you need to multiply this with the x of 0. So, same matrix, but you have x of 0 as 1 and 0 here. So, the phi of t is 2 by 1 matrix, 2 by 1 matrix, and this is also 2 row 2 by 1. So, you need to multiply this e power at into 1 0. So, the resultant response 0 initial response, when you call this as, you get 2 e power minus t minus 1 e power minus 2t and minus 2 e power minus t plus 2 e power minus 2t. So, this is the 0 initial response you get for the given system, and you need to have a 0 state response also. This is nothing but Laplace inverse of phi of s into b times u of s. So, u of s is the input matrix that is you have here. So, this is u of s, then b matrix, b is the input matrix that is already given as 0 and 5. So, we need to get now 0 state response. So, for this Laplace inverse of s plus 3 by s plus 1 into s plus 2, 1 by s plus 1 into s plus 2, minus 2 by s plus 1 into s plus 2, then 1 by s by s plus 1 into s plus 2. So, this is phi of s. Now, B matrix is 0 and 5. This is called as input matrix, and U of s is the unit step input. U of s is the unit step input. So, you need to have 1 by s, you need to multiply with that. So, you have phi of s, then B of s and U of s. So, and you need to obtain the Laplace inverse of that. So, you get 0 state response after getting the Laplace inverse of state transition matrix, then B input matrix multiplied by unit step signal U of s. So, in time domain or in time function, you get this phi by 2 minus phi e power minus t plus phi by 2 e power minus 2t, and the second component is this. So, this part is known as 0 state response, and due to initial conditions you have got 0 initial response as this matrix. Now, the complete time response x of t is equal to sum of ZIR and 0 state response. So, you need to add these two matrices to get x of t, that is the complete time response. So, this is the matrix you get x of t, and this is the solution, complete solution of the state equation. Now, to get the output equation, y is equal to c into x of t, which you got here. So, c is given in the problem. This is known as output matrix, c is known as output matrix 0 1, and x of t, that is actually given here 5 by 2 minus 3 e power minus t plus 3 by 2 e power minus 2t and 3 e power minus t minus 3 e power minus 2t. So, this with output matrix you need to multiply the x of t. So, you have 0 here. So, the first component will go and only the second component will remain, that is 3 e power minus t minus 3 e power minus 2t. So, this is nothing but 3 e power minus t minus e power minus 2t is the output solution, output of the equation that is given. There are two parameters to check the system stability when state equation is given. So, the two parameters are controllability and observability. these are the two indices that are used to say that whether the given system is good or bad in terms of controllability and observability in the state space analysis. So, what exactly is the controllability? So, a linear system, when it is described by the state equation x dot is equal to ax plus bu and y is equal to cx plus du. This is the state model. So, if there exists an input vector u of t which transfers the state of the system from initial state x of t0 to x of tf, if there exists an input vector which can actually take the system from x of t0 to x of tf in a finite interval or finite time, then we say that the system is controllable. Controllability is if there exists an input vector u of t to take the system from x of t0 to x of tf in a finite time, that is important, in a finite time, then we say that the system is controllable. So, there is a simple test to check this controllability in the state space analysis, and this is called controllability test. So, this test, when a nth order system is given, how to check the system given is controllable or not. So, for that there is a composite matrix, we need to form or create that is called QC, composite matrix, and the elements of this matrix are B, AB, A square B and so on, A square B and up to A power n minus 1 into B. So, the rank of this matrix, the controllability test is the rank of this matrix is n, then we say that the system is controllable. So, how to obtain these components is from the state equation, because controllability is there is an input vector which is taking the system state from x of t0 to x of tf. That is why we use only the matrices of the state equation. You can see B is the input matrix and A is the state matrix. So, B, AB, A square B and so on. So, it can go up to A power n minus 1 into B. So, the rank of that matrix should be n, then we say that the system is controllable. So, it must have determinant, then we say that it is controllable. Next, observability is the another parameter of the state space analysis. Observability, this is the linear system, again x dot equal to ax plus bu and y is equal to cx plus du is completely observable, if the knowledge of the inputs and outputs, in finite interval, that is t0 to tf, are sufficient to determine the state, of the system, every state of the system. So, the knowledge of inputs and outputs must be helpful, should be sufficient in this finite time interval to determine the every state of the system, then we can say that it is system is observable. So, for this also there is a test, observability test. For this you need to have a matrix again Q0, and the components of this Q0 is C matrix is the output matrix, then CA the second component, then C A square and so on. Observability matrix is again with the help of output matrix and state matrix it is formed. So, this also can be written as C as the first component, then C transpose and A transpose, and the third component C transpose A square transpose and so on. So, the rank of this Q naught, that is observability matrix, also should be n, then we say that system is observable. So, for both QC and Q0 we need to have the information of A, B and C, that is state matrix and input matrix and output matrix, so that QC and Q naught should be obtained with the help of those matrices, and we must see that the rank is n for both the matrices, then we say that the given system is controllable as well as observable. So, to check the controllability of the system, there are two things given, one is state controllability and the other one is output controllability. So, the formula that is used for state controllability is you need to form QC controllability matrix. For that the elements are B, then AB and A square B and so on. As this is 2 by 2 matrix, so two components are enough to see the state controllability B and AB. Similarly, if you want to see the output controllability with the help of this output controllability, this is given by the elements, you need to multiply the QC by C matrix, where C matrix is the output matrix. So, to check the output controllability, you need to form the matrix again, and the components are additionally, when you look at this, C will be the additional component, CB, then CAB. This is what you should get for the output controllability. So, mathematically what is that you need to see for both these matrices is the rank is 2. That means this must have some determinant, non-zero determinant, then we say the system is controllable. So, to see QC, the two elements are B and then AB. So, B is already given, AB we need to have. So, what is AB? A is given and B is given, product of that. A is 0, 1, minus 1, minus 3. This is A. Then B is 1, 2. So, what is the dimension of this matrix? It is 2 by 2 and this is 2 rows and 1 column. So, you need to have AB, this is equal to 0 plus 2 and this is minus 1 and minus 6. So, minus 7. So, 2 and minus 7 is AB. Now, B is already given here in the system 1 and 2, and AB is this one you obtained 2 and minus 7. So, what is the rank of this matrix? That means you need to find the determinant. So, determinant minus 7 and minus 4, this is equal to minus 11, not equal to 0, not equal to 0. So, we say that the rank of this matrix is 2. So, as this is 2 by 2, so the rank is 2. So, we say that it is a state controllable. The system is state controllable. So, when you have a rank of this matrix as 2, and to see that output controllability, you should have CB and CAB. So, the elements of CB, C matrix is multiplied by B matrix, you will get 3, and CAB is minus 5, and the rank is 1. So, we say that even this output controllability, it is output controllable, that system is output controllable because there is a rank for that matrix. So, we write it is output controllable. So, this is the way the controllability test is performed to check the system status. So, now the system complexity is slightly more, that the A matrix is given 3 cross 3 and B is 3 cross 1 and C is 1 cross 3, and the question is check the system state controllability, So, as you have now 3 by 3, so to see the composite matrix or to form the composite matrix, there will be 3 components in it. Starts with B, first component, then AB is the second component, and third you have A square B also in this. So, this rank of this matrix must be 3, then we will say that system is state controllable. So, that we need to check. So, B is already available, that is given in the system itself, but you need to find out what is AB. So, for that AB you need to have A is given here, B is given here. So, product of A and B, 1 2 1 0 1 0 1 minus 4 3 is A, then B is 0 0 1. So, this resultant product of these two is AB, you get 1 0 3. AB is, this is 3 cross 3 and this is 3 cross 1. So, you will get 3 cross 1 as the resultant. Now, A square B, that means A should be multiplied by AB. AB is already obtained here, A is known. So, A square B I use this way, A into AB, where A matrix is given here 1 2 1 0 1 0 1 minus 4 3, then AB is here, you have 1 0 3. So, this resultant is A square B is equal to 4 0 10. This is again 3 cross 1. So, you got B, AB and A square B. Now, you need to arrange them in a QC. So, QC is equal to, the first component is B. B is given here 0 0 1, and the AB you got here 1 0 3, and A square B you got 4 0 and 10. So, the rank of this matrix should be 3, but it is not so here. If you see the determinant of this 0 into, this is anyway 0, now minus 1 into, again this is 0, and plus 4 into, again this is 0 and 0. So, we say that it is singular, that means the rank is 1. So, this is not controllable. We can say that system state controllability, it is non controllable because rank is not 3 here, So, you get the determinant as 0. So, we say that it is not state controllable, it is not state controllable. So, this is now data given to see the state observability. So, whether the given system state observable or not. So, we need to have the observability matrix here Q0, and the components of this are C transpose, then C transpose A transpose. Observability matrix is with the help of state matrix and output matrix, whose transposition also you need to determine. So, C is given as 1 0. So, C transpose is 1 0 this way. Okay. Now, C transpose into A transpose. So, first you need to know what is A transpose, because A is given here -2 0 and 0 and -1. So, we write A transpose as -2 0 and 0 and -1. Rows are columns in transpose. Now, we need to get C transpose into A transpose, that is the second component of the observability matrix. So, to get this, C transpose is 1 0 and A transpose is -2 0 0 and -1. So, now arrange them in the observability matrix. You got C transpose as 1 0 and C transpose into A transpose, you get -2 and 0. This is observability matrix. Now, if you see the determinant, you get 0. So, we say that it is again singular, because rank of this matrix should be equal to 2, but it is not so, because you get the determinant 0. So, we say that it is singular, and hence it is system that is given is not observable. So, forming the matrix, observability matrix, and then find out the components of that, and with the help of that find out the determinant. So, if determinant exists, we say that rank is 2, but it is not so. So, we say it is singular and it is not observable.